Hi, and welcome to chapter 7.2, where we are talking about sample proportions. In this topic, you should be able to find the mean and standard deviation of the sampling distribution of a sample proportion, or what you call p hat. We should also be able to check the 10% condition before calculating our standard deviation of the sample proportion. So basically, the standard deviation of p hat. Can you check the 10% condition? If you don't remember the 10% condition, I have a definition at the very end of our video set here. You can also determine if the sampling distribution of a sample proportion is approximately normal. And if it's normal, we're going to use the normal distribution to calculate probabilities involving sample proportion. So you have to first test if it's normal, and then you can use normal distribution formulas. So first and foremost, let's talk about the sampling distribution of p hat. And we're going to ask ourselves, how good is the statistic p hat is an estimate of the parameter p? So in essence, how good is the information or characteristic about the sample? How good of an estimator is that back to the population? So the sampling distribution of p hat will answer this question. So we're going to consider a Rhesus Pieces simulation. We're going to do a little bit of this in class as well, but just kind of a preview or a reset for some of you. We're going to do a bunch of simple random samples of Reese's Pieces from a population, and we're going to look at the proportion of orange candies at either 45% or 15%. So we launched an applet, and it's called the Rothman Chance applet, and so we're going to do this in class, but you can also check on page 441 of your textbook if you want to review this. But I went ahead and pulled these images for us. So if I'm looking at a sample size of 25, I drew 25 Reese's Pieces from this candy machine. And I'm looking at a p-value of 0.45. Okay, they represent it as pi on the applet, but we know that this is p. Then what do you notice about it? Well, my mean is 0.448. Hey, that's pretty darn close. And my standard deviation is 103. And the number of samples that we drew, and we're going to draw on each of these simulations, is 400. So this is the dot plot of 400 different simulations, each with a sample size of 25. And we're testing the theory that our oranges, we're testing that we know that we have an orange proportion of 0.45. So if you're looking at just the orange candies, that's our dot plot. Cool. Well, let's compare it to what happens when my sample size increases to 50. Well, let's check out our mean. Our mean got even closer from 0.448 comparing to 0.450 to 0.451 comparing to 0.450. Hey, look at that. We also see something else occurring. Look at your standard deviation when you have a sample size of 25. It's at 0.1. Look at your standard deviation when you increase your sample size. It goes to 0.06. So here's further proof that as you increase the sample size itself, we didn't increase how many samples we drew. That could affect us as well. But we increased the sample size itself. What happened to our spread? Our variability got closer. So our variability lowered. That's a good thing. We want that to happen. Now let's look at 0.15. So we're looking at now a new set of candies where you originally have a probability of 15% are orange. So if I draw a sample size of 25, 400 of those samples, look what happens. Okay, so if I look at my dot plot of all 400, the sample distribution, I notice that my p-value is still about center of this distribution. But if I go back, look at this distribution. Pretty darn symmetric, and it's about bimodal, or it's at that peak is approximately our p-value. My peak is about occurring at 0.45 in both of them. Here, my peak is now occurring closer to 0.15, and it skewed it a little bit right, didn't it? Because our greater volume of numbers are between that 0.1 and that 0.2. So it skewed it a little bit right. And even here, we can kind of see slightly skewed to the right. We could still call it a little bit symmetric or roughly symmetric, but you can see that your p-value has greatly shifted. The previous two images, it was at about 0.45. In these, it's about 0.15. So what do we notice? What have we learned? we've learned that we can describe each of these. We can cuss them out, right? We can talk about their center. When we took the 0.45, we had a center about 0.45. When we took the standard deviation, though, if we talk about their spread, we can see that our standard deviation shrunk. It got lower because our variability lowered as our sample size got bigger. You can see the same thing occurring here. My mean is pretty darn close, and it's a heck of a lot closer as I increase the sample size. My standard deviation is pretty low, but it's even lower when I increase my sample size. So what do you notice about these three main concepts? Let's talk about these very quickly. What do you notice about the shape when we're talking about sampling distributions? In a lot of cases, your sample distribution of p hat will be approximately normal. We kind of saw that, about asymmetrical, about bell-shaped. This seems to depend on the sample size. So the larger your sample size, the more normalized your curve might become, and the population proportion of P. So if my proportion was about 0.5, then it was a really nice bell curve because my peak is going to be occurring at the halfway point. But when our proportion was 0.15, it shifted towards those lower values. Of course it did, because my balance point, my tipping point, my peak, my highest point, however you want to see that, is going to shift towards that population proportion p value. My center, the mean of the distribution, so the mu of p hat was equivalent to about the p value. So we saw this. Hey, isn't that what we want for an unbiased estimator? For an unbiased estimator, it must be equivalent to the mean of the distribution. And since our p value was, and our p hat value in each sample proportion was very close, we could say that our p hat value was an unbiased estimator. Again, why? Because it's equivalent to the mean of the distribution, sample distribution. And finally, spread. We noticed that our standard deviation got smaller as our sample sizes got larger. So in essence, our standard deviation of p hat is going to both depend on our sample size as well as the original proportion value. So just kind of notice what happens to center, spread, and shape as you talk about and describe sampling distributions. There's another very important connection. So when we talked about the candy machine example, we started by taking repeated number of SRSs. We did 400 of them, right? We first started with 25 at a p-value of 45. Then we went to 50 at a p-value of 45. Then we moved to 25 at a p-value of 0.15 and 50 trials at a p-value of 0.15 as well. For any sample, we can think of each candy that comes out of the machine as its own trial of chance process. A success occurs when we get the orange candy. So if we let X be the number of orange candies obtained, hey, we've seen X before when we talked about random variables. So there is a relationship between the binomial count X and the sampling distribution of p hat. And we actually see it right here. P hat can be equivalent to the count of successes in your sample, so your X divided by the size of your sample. Really cool. We have a connection there. But let's further continue talking about this. If we go back to chapter 6 and we really recall the binomial random variable, so this particular simulation met a bins, and so we remembered that because it's a bins, you have your own unique formulas, very simple formulas when you're calculating the mean and when you're calculating a standard deviation, and they're simply based on your sample size times your proportion, or with standard deviation, sample size proportion times the anti-proportion, right, the one minus your p-value. So this is, there's just some verbiage about it, but let's continue on. Since we know this formula, and we know this formula, and I just told you that p hat can be written as x divided by m, or 1 over n divided times x. It's the same formula right here. X over n is equivalent to 1 over n times x. That's what they're saying. We're just multiplying your random variable by the constant. So because of that, we can derive some more formulas. We can derive that the sample, or the mean of p hat would be equivalent to 1 over your sample size times your proportion, and that would be equivalent back to your p value. So this means that you have an unbiased estimator of p. We could also look at our standard deviation in the same way. So again, we're basing it off of this formula and this formula. We derived these new formulas. I do have to triple check if these are on the formula chart. However, 9 times out of 10, we're not really memorizing just basic formulas. More often than not, these are provided, and it's about can you utilize and apply them. So here is just a very brief wrap-up of all of that, and in a nicer, neater package for you. So if I'm talking about sampling distributions of a sample proportion, we can summarize all that information. When we choose an SRS of size n from a population with original size n, with a proportion of p being your successes, then we can let p hat be the sample proportion of successes. So if it follows all of those rules, then our mean of the sampling distribution is simply p hat. So they're saying that your mu value is equivalent to your p hat value, and that's because you have that unbiased estimator. And your standard deviation is equivalent to this formula. But again, you have to meet the 10% condition, aka your sample is no greater than 10% of the population. So let's wrap up. As n increases, the sampling distribution of p hat becomes approximately normal. So again, as your sample size gets bigger, your distribution becomes more normal shaped. If it's normal shaped and you check the condition, the 10% condition, then you can use these calculations instead. So here is a little wrap-up image of that in visual format. So if you have a simple random sample size n, simple random sample size n, simple random sample coming from this proportion of individuals, then we can display it as such. So they're showing you the formula of the standard deviation. They're telling you that your mean value, and again, it follows the normal distribution curve. And so this just kind of hopefully helps you rehash the big idea of sampling distributions. I'll say the mean of the sampling distribution of p hat is the true value of the population proportion p. So the standard deviation of p hat will get smaller as the sample size n increases. So just kind of a wrap up of what we just talked about. Make sure that you are recognizing both the large counts condition and the 10% condition. For those of you who don't know what those are, I have a wrap up in the very next brief little baby video. But in the meantime, you've got a quick check your understanding to do as for yourself. So get working on that.